In this lab, we are going to be configuring control plane policing and control plane protection for router 2, which you can see in the topology in CML. We can reach router 2 through this external connection from the Kali host. So we are going to use this to send packets to router 2. So with control plane policing, we can basically rate limit the control plane traffic destined to the router itself, like for example ICMP, SSH or SNMP, and also routing protocols like BGP, OSPF or EIGRP. The control plane traffic is always process switched. The main benefit of control plane policing is that we can protect the CPU of the router against denial of service attacks by limiting the traffic that can reach the router's CPU. So if the CPU has to deal with a large number of process switch packets, that can also affect the data plane traffic. Because if the resources of the router are exhausted by the large number of control plane packets, the CPU utilization goes very high, and the router basically cannot maintain the neighbor relationships for any kind of routing protocol like OSPF, EIGRP, or like LDP. And if the control plane is broken, the data plane is also gonna be broken. So in this lab, we are gonna be walking through the steps that are necessary to configure control plane policing and also control plane protection, which is an extension of control plane policing. So in this demonstration, we are going to limit the ICMP and the SSH traffic destined to router 2, and we are going to use the Kali host to send packets to router 2. So the first step is to create an access list to identify the traffic that we want to rate limit. So IP access list extended, and we are going to call this ICMP underscore SSH, and we need a permit statement for ICMP echoes, and the source is gonna be any, and the destination is the IP address of interface G00, which is host 10.10.20.172, and we want to limit ICMP echoes. And similarly, we create another permit statement for SSH traffic, which is TCP based from any source and destined to the IP address 10.10.20.172, and the destination port is gonna be TCP port 22. And that's all we need for this example. There is an implicit deny at the end, of course, but that doesn't mean that all other control plane traffic will be dropped, like OSPF or BGP. We don't have a permit statement for BGP, for example, but it simply means that other traffic is not gonna be policed or rate limited. Next, we create a class map, and I'm gonna name this simply class map 1. And here we have many options to identify the traffic, like we could use DHCP values, for example, but we are going to refer back to the ACL, which we have just created. So match access group, and the name was ICMP underscore SSH. And now we are going to create a policy map, and let's call this CoPP. The traffic class is gonna be the class map 1, which is what we have just created. And here we are going to police the traffic, so we can define the value in bits per second or kilobits per second, which is what we usually do. But here I'm gonna define the value in packets per second because it's easier to demonstrate. So the police rate is gonna be 5 PPS, and the conform action. So what are we doing if the rate of the control plane traffic doesn't exceed this value? We transmit the traffic like we normally do, and the violate action. So if we exceed this rate, the 5 packets per second, we drop the traffic. And we are done. Next, we apply this policy map to the control plane interface. But before we do that, let's see the response of the router without the control plane policing. So first, from the Kali host, let's ping the router, and the interval between the echo requests is gonna be 0.1 second, which is about 10 packets per second. So this will definitely exceed our policing rate, but the policy map has not been applied yet, so this should work. And as we can see, we have an echo response for each echo request. And to test the SSH traffic, we are going to use a hacking tool called hping3, which is used for denial of service attacks. And we are going to send TCP packets with the SYN bit set to the router to the port 22, and with the fast option, we send packets at the rate of 10 packets per second. So this should work for now, but after applying the policy map, we should also drop SSH traffic. And I'm gonna open a Wireshark. And we can see that for each SYN packet, the router sent back a SYNAC. So we can use this tool to perform denial of service attacks against the router if we send the SYNs at a very high rate. But now let's apply the policy map and check if it works. So we apply the policy map on a logical interface called control plane. And service policy input and the name was CoPP, and we can verify this with the command show policy map, control plane, and at this point we have 0 packets dropped because of rate limit violation. But let's run the hping again. And we can see that we don't have a response for each SYN packet. We have sent 58 packets, but received only 19 packets. And that's 68% packet loss. Let's also run the ping command again. And we can also see that we have a few drops here and there based on the sequence numbers. And overall, we have a 60% of packet loss. And that's because the control plane policing. So by doing this, we can limit the number of packets which can reach the router's CPU and protect the router from denial of service attacks. We can also verify this on the router, show policy map control plane. And now we have 84 packets dropped because of violation. And now let's take a look at control plane protection. So control plane protection is an enhanced version of control plane policing, and we divide the control plane logical interface into 3 sub-interfaces. And in this lab, we are gonna be focusing on the host sub-interface, because that is responsible for the traffic destined to the router itself. And in this video, I'm gonna show the port filtering on the host sub-interface, because it's the easiest to demonstrate. So we have some open ports on the router. We can verify that with the command show control plane host open ports. So we have a telnet running on the router, SSH, HTTP and HTTPS. So these are the open ports. We have services listening on these ports. But what about the closed ports? If we get a SYN packet on a closed port, what do we do with that? Does the router generate a response for that packet, or just drops that packet silently, and it doesn't even reach the CPU of the router? So let's check that. Again, we will use hping 3, and let's pick a close port. For example, TCP 25, and let's send a SYN to this port. And indeed, we get a response back with reset and the egg flag set, indicating that this port is closed. So we can also use closed ports for denial of service attacks to exhaust the resources of the router and to generate high CPU utilization if we send these packets at a very high rate. Now our goal is to drop these packets early and silently before they hit the CPU. And if we do this, the router obviously won't generate a reset for each TCP packet, because these packets don't even reach the CPU. So by doing this, we can also protect the router from denial of service attacks. So first we need a class map again with the type port filter and match any, because we are gonna be using multiple mesh statements, and let's call this simply port filter and match the closed ports. So this is everything which isn't open, so everything besides these. And let's also match TCP port 80, which is open, but let's also drop packets destined to TCP port 80. And we create a policy map again, or policy map type port filter, and let's call this CPPr. The class is gonna be the class map which we have just created, or class port filter, and we drop the packets before forwarding it to the CPU. And let's also log everything just for verification purposes. And again, we apply the policy map to the host subinterface of the control plane. So control plane host and service policy with the type port filter input, and the name was CPPr. And let's confirm. We use the same hping command as before. And this time, no answer from the router. So the router just drops these packets silently. And let's also verify it on port 80, which is open, but still we should drop the packets destined to TCP port 80, which is what we do. And let's also test an open port, which we should be able to reach. So port 443, HTTPS, for example. And indeed, we are receiving SYNAX from TCP port 443. So this is how control plane protection and port filtering works. We can also confirm on the router some syslog messages have been generated for each dropped packet. So this is how we can use control plane policing and control plane protection to protect the router's CPU against denial of service attacks, and to limit the control plane traffic which can reach the router's CPU.